Okay, good morning. My name's Ken Howard, and I'm representing Irish University in Denmark, but also we've got a spin-out company based around this technology. And basically, the technology provides delivery solutions for RNAi therapeutics, which is an exciting new drug that is just crying out for better delivery systems. Okay, in a nutshell, genes via the messenger RNA produce proteins. In certain conditions, overproduction of those proteins, such as TNF-alpha in arthritis or the assembly of viral proteins, can cause disease conditions. Genes can be silenced at the messenger RNA level to interrupt the production of these proteins and alleviate this disease condition. And this occurs by a natural process called RNA interference, which occurs through small interfering RNA, which are double-stranded RNA molecules, less than 30 base pairs. And the beauty of this system is the actual specificity, should I say, of the material. So it works inside the cell by a cascade of events. Essentially, double-stranded RNA is chopped into smaller fragments, and then one of the strands guides an enzyme complex to the homologous sequence on the messenger RNA. So what you get is specific knockdown of that messenger RNA. So you can design siRNA to be specific for only one type of messenger RNA, so you only interrupt the production of that particular protein. It's a highly specific drug. However, delivery is a bottleneck. And big pharma are crying out for delivery solutions to optimize, or should I say utilize, the investment that they're placing on this technology. At the University of Aarhus, what we've done is we've created a conceptually simple nanoparticle system composed of the polysaccharide chitosan that interacts with the siRNA to form these nanoparticles. It's a very simple system. A plus B gives these nanoparticles. And we've got different applications for these nanoparticles delivering the siRNA, and we're utilizing the bioadhesive properties of the chitosan, so they can penetrate the mucosal barrier for pulmonary delivery, for example, in the lung. So they can overcome the physical and the mucus layer that overlies the ciliated epithelium. And what chitosan can do is it's mucoadhesive and mucopermeable, so it's able to penetrate these surfaces and deliver the siRNA, as opposed to normal particulates that are swept away. We've taken these into our model system, which is a transgenic green mouse, and as you can see, this is a section of the lung after we've administered intranasally chitosan systems containing siRNA that targets the green fluorescent protein. So we've got an siRNA that targets or knocks down the green protein. And on the right, you can see reduction of fluorescence around the bronchial epithelium, which is due to the siRNA. When we use a control siRNA, so one that doesn't target the messenger RNA of the EGFP, we see retained integrity of production of the EGFP. So what we're showing in this model system is in the lung we can target and knock down a gene. We've taken this forward in an aerosolized form and working with partners in Berlin on influenza. A second strategy for this system is where we try and target anti-inflammatory disorders by loading up macrophages that produce inflammatory cytokines and knock down, for example, TNF-alpha. And our approach is a simple one. We go intraperitoneally this time, not mucosally. And you can see that when we fish out the macrophages, they're loaded with the particles. And what you can see in an inflamed tissue at a distant site, that the macrophages migrate into these regions. We've tried this in two preclinical animal models. One for radiation-induced fibrosis, again caused by the pro-inflammatory TNF-alpha. And you can see that when we administer our anti-TNF-alpha chitosan nanoparticles, we get no production of the fibrotic condition, whereas when we use control siRNA, they become fibrotic. Final slide showing our studies in rheumatoid arthritis, a chronic inflammatory disorder, which causes disruption of the cartilage. When we administered our anti-TNF-alpha nanoparticles, we get retained cartilage here, opposed to the control where you get disruption of the cartilage. And we've got a spin-out company called Nanoference, which is utilizing this technology. Sorry to run over time.
Thank you very much. Very interesting.